Okay, here we are for section 4B, thermodynamic aspects of phase transitions. Okie dokie. So, from the last chapter, we saw that dG, right, Gibbs free energy, is equal to VdP minus SdT, right? And as stated at the beginning of this chapter, our chemical potential, mu, is the same thing as G, right? So in that case, mu is equal to VdP minus SdT, right? So in this case, mu equals VdP minus SdT, right? If we're at constant pressure, then all of this cancels out, and mu over, or d mu, we'll call this uh, d mu over dt equals negative S, right? Or negative molar entropy in this case. I'm going to make it molar. Okay. And same thing, if temperature is held constant, now mu is equal to VdP with rearranges to being mu over, or d mu over dP equaling the molar volume. All right. So these are two little things that are going to help us basically do a little bit of math on it. All right. But we're looking at how our chemical potential changes with pressure and temperature, basically. That's what we're looking at here, right? And it's going to exist in the phase which has the lowest mu at any given temperature and pressure. Right? If T or P change, a new phase may have a lower mu value, and the species will transition to it if it is kinetically feasible. This is one other thing we don't talk about too much, right? But for every transition or reaction or anything like that, there's two levers. There's thermodynamics and then there's kinetics. Like, so for instance, it is thermodynamically favorable for a diamond to unwind, if you want to call it that, and become pure regular graphite, like pencil lead. All right, thermodynamically, that is what is spontaneously happening, right? But kinetically, it's going to take hundreds of thousands or millions of years for that to actually happen, right? Because kinetically, these things are just kind of locked into position too much, right? They're going to take too long to get out of position. And so that's why we say diamonds are forever. All right, technically they are going to uh, disintegrate, right? But they're going to take so long in the human time scale, it's not a big deal. Now we can use these two equations, right? An example here, right? This iron is heated from 100 degrees Celsius to 150 degrees Celsius. But how much did the chemical potential change, right? If we take our molar entropy of iron to be 53 joules per mole Kelvin over the entire range, right, again, that's not necessarily going to be true, but it's going to make our math much, much simpler, right? Well, our negative molar entropy is going to be equal to d mu over dt, right? But we just saw d mu over dt at constant pressure, right? Don't worry about the constant pressure. We're going to assume this, right? So our negative entropy is negative 53 joules per mole Kelvin, right? Over here, we'll just do d mu, make it a little bit simpler, right? The change in mu basically is going to be over the change in temperature, which is 100 degrees Celsius to 150 degrees Celsius, right? Now, we don't need to change this to Kelvin because this is a change, right? A change in Kelvin is the same thing as a change in Celsius, right? So this is 50 Kelvin, 50 Celsius, same difference, right? Same difference, right? And when you do that little bit, you would see that the change in mu would be equal to 53 divided by 50, which is 1.06 joules per mole, right? 1.6 joules per mole, right? So a very, very small amount, right? Very, very small amount, right? Which is what you would sort of expect, right? This is iron, solid iron in this range, right? It stays solid, right? And nothing really changing all that much, right? So the entropy is going, or the chemical potential is not going to change all that much. The same phase, right? So the same phase. So we wouldn't expect that much of a potential change. Right? Now, if we look at how these changes go, right? If we look at entropy and its temperature and its effects on mu, right? So we know that entropy always has to be positive for all substances, right? Absolute entropy has to be positive, right? So that means this side is always negative, right? Right. The left-hand side always has to be negative, right? Which means that if we increase T, right, we always must end up with a decrease in the chemical potential. That reminds me real quick. Let's do this correctly. We forgot the negative. We forgot to carry the negative down, right? So it's negative 1.06 joules per mole, right? That's our change in chemical potential. Right. So anyways, as we increase T, right, we must always result in a decrease in chemical potential, right? So generally, right, and generally, I should say, right, the entropy of our gas is much greater than that of our liquid or a solid. That one's pretty straightforward, right? So what that means is that as we go from solid to liquid to gas, right, you see here, the slopes of the lines are changing, right? The slopes of the lines are changing. And so here in the vapor phase, when we have a high value of entropy, we expect changing temperature to have a big effect, right? A very steep slope, right? In the solid phase, when the entropy is low, we expect a change in temperature to have a lesser effect on the chemical potential, right? And again, wherever we are in this line, whichever phase has the lowest chemical potential is the phase that that substance is going to be at, right? In terms of temperature here. Yeah. Now, if we do something similar with the molar volume, right? Our molar volume, again, always has to be positive because we can't have a negative volume, right? That doesn't make any sense, right? Volume always has to be a positive number, right? So if this is a positive number, the right-hand side always needs to be in positive, right? So an increase in pressure always results in an increase in chemical potential. All right, increase in pressure always results in an increase in chemical potential, right? And generally, right, the molar volume of a gas is going to be, I should have put in like two arrows here, much, much bigger than the molar volume of the liquid, which is generally going to be bigger than the molar volume of the solid, right? One notable exception here is water, right? Water, the molar volume of ice is bigger than that of liquid water, right? But generally, that's going to be the thing, right? Now, when we look at these examples here, right? So we have two examples here. We have low pressure and high pressure, solid versus liquid, right? Solid is in the solid lines, the liquid is in the more faint dotted lines, I should say, right? As we go from low pressure to high pressure, right, we see a certain change in this case, the freezing point, right? So our transition for freezing or fusion here, right, is where the solid and the liquid phase meet, right? Where the solid and the liquid phase meet. So in this low temperature kind of purple line, right, the solid phase and the liquid phase meet at this particular temperature, right? As we increase the pressure, right, we see solid blue now meets dotted blue for high pressure at a higher temperature, right? And so again, as we've increased the temperature, we change the fusion point, the point of fusion. Right? This on the right-hand side is for water. We see things that are a little bit kind of crazy, right? If we look low temperature or low pressure, we have a certain freezing point, right? And then for high temperature or high pressure, I should say, right, the blue solid line and goes below the liquid line, okay, which is kind of weird, right? But the freezing point actually decreases for in this example for water, right? Now again, put these together, right? We see that increase in pressure always results in an increase in mu, right? Because Vm always has to be positive, right? Always, 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 always positive. The only question is how much is it increasing, right? Now, for vapor pressure, the next particular thing, right? Vapor pressure again is the uh, partial pressure of the gas in equilibrium with its condensed phase, which will be solid or liquid. Right. Now we can apply pressure to a solution two different ways. We can do it mechanically, like if we had a piston and we were just pushing on it, or we can put in an inert gas and increase the pressure that way. Right. Right. If we do it mechanically, then the vapor pressure, the pressure of gas is just the vapor pressure. Right. If we put in an inert gas, now it becomes the partial vapor pressure, right? Because you have the pressure of the vapor and the pressure of the inert gas, right? And so this becomes a partial vapor pressure, but really it's going to be mostly the same. All right. One thing to note here is that in our little derivation, what we're going to do, our partial vapor is going to be P lowercase. Right. It's going to be kind of hard to, I'll try to do something to put it together. And then P uppercase is going to be the total pressure. Okay. Or the applied pressure, really. I'll try to do something. I'll give P uppercase like this little thing just to make it easier, right? Because again, when you see it in print, it's pretty obvious, right? But when I'm writing it like this, I don't know how to draw a lowercase p and an uppercase p differently when they're in the middle of space. All right. So it says when pressure is applied, the partial vapor pressure increases because molecules are squeezed out of the condensed phase. Okay. So if we wanted to put this together, right, vapor pressure, right, is going to exist at equilibrium when mu of the liquid phase equals mu of the vapor phase. We'll call it gas. Right? They have to equal to each other. Yeah. Right. Now, this is going to be at constant temperature. Right. Constant temperature. We're going to keep it we're going to change the pressure, but at constant temperature. Okay. So when the pressure on the liquid is increased by a certain amount, right, dP, the chemical potential of the liquid changes by Vm dP, right? This is just, right, this particular equation here rearranged, right? Vm times dP gets you du, the change in the chemical potential, right? Vm of the liquid, let me put that there. Vm of the liquid times dP. All right, keep in mind this is capital P. All right, for the total pressure, dP, capital P, total pressure. Right. For the gas, right, the gas of our, or for the gas, mu of our gas is still going to be Vm of the gas times dP, right? But because our gas molar volume can change so much, right, what we're going to do is that we're going to say that we're not going to do molar volume, right? We are going to do RT over P, like lowercase p times dP, right? And this is the partial pressure of just the gas by itself, right? Not the total pressure, just the partial pressure of the gas by itself. right? And again, because we're at equilibrium, these two things have to equal each other. Right? If we weren't at equilibrium, then we wouldn't have this problem, right? But since we're at equilibrium, they have to be equal. Now, from here, all right, from here, we can integrate these things into different functions here, right? So when there's no additional pressure acting on a liquid, let's move out from here. Next one. When there's no additional pressure acting on the liquid, P, which is the pressure, capital P, so the pressure experienced by the liquid is equal to the normal vapor pressure of P naught, right? So again, so if we have an instance of no inert gas, right, then capital P is equal to little p, basically, or we'll call it P naught, which is going to be the normal vapor pressure, right? Right. And as such, the vapor pressure is also going to be equal to the normal vapor pressure in these particular circumstances, right? Right. So our total pressure, of course, is going to be our total pressure is going to be the partial pressure plus the change, how much extra additional pressure we're going to add in, right? So if the effect on the vapor, the pressure, if the effect of pressure on the vapor pressure is small, like basically what we're saying is that if we can assume this P stays the same number, no matter how big, how much additional pressure we add in, right? Then a good approximation is to replace this small p, right, by P star. All right, basically what we're saying is that we're going to assume this is the normal vapor pressure, and we're going to assume that it's not being affected by the additional pressure, right? So we're keeping it as simple as possible, right? And so when we're trying to do this, if we look at what we had before, let's see which side I had everything on, right? So on this side, we had Vm of our liquid times dP of the total pressure, right? Right. And over on the right-hand side, we had RT over little p times dP, right? Partial pressure. Right. If we start to integrate these things, right, we're going to integrate over basically the change in pressure, if you want to call it that. Right. So on the left-hand side, we would have an integral going from original P, right, capital P, right, to now, oh, sorry, not capital P, but original vapor pressure, right, because our capital P is vapor pressure, the normal vapor pressure plus the change. We're going from the normal vapor pressure to the normal vapor pressure plus the change, right, the additional pressure here, right? Vm, we're going to assume is going to be constant, and for a liquid, it is going to be basically constant, right? And then we're just gonna have dP, right? That one's pretty easy right there. On the right-hand side, right, we would have RT, right? Those are constants. The integral here is going to be from P, the normal vapor pressure to the regular vapor pressure here, if you want to call it that. Right. Right. Now from here, oh, and we forgot about dP over P, right? Now we can rearrange things to different sides, right? If we do this side, it would be RT, right? This integral becomes the natural log of P over P naught, or the normal vapor pressure. Right, that one's pretty easy. All right, and then over here, this would be Vm of our liquid, right, equal to basically, delta P here, the change in pressure, right? Again, we're assuming big pressure, change in big pressure, right? We're assuming that this change is much greater than the change in P, right? If we plug this in, like you would have P2 minus P1, right? Right. Well, P2 would be P naught plus delta P. And then P1 would be P naught. Well, if we assume P naught and P naught are the same, they cancel each other out. You're left with only delta P. Right. And if we rearrange a little bit, right, we can get Vm of our liquid over RT is equal to delta P, which is, again, it's the additional pressure. It's going to be equal to the natural log of P over P naught. Right? And P naught, again, is the normal vapor pressure of that liquid, of that compound. Right? Now, if we really want it to be super crazy, this is the one that I'm going to prefer to use, honestly, because it's nicer to me. Right? If you really want to be super crazy and do a different equation, we can rearrange everything, right? Get rid of the natural log, again, for whatever reason, where the partial pressure, right, would change by taking the normal vapor pressure times E to the Vm delta P over RT, right? Again, if you take this whole thing and rearrange it, that's what you would get. Maybe that's a more useful form for you. But for me, I think it's kind of annoying, to be honest. I don't like using E like that. I'm much more comfortable with natural log, to be honest, and working with natural log. That's what I'm going to stick with. Right. So let's use that. All right. We have a pressure exerted on water at 20 degrees Celsius with a piston. All right. The vapor pressure of water is 2.34 kilopascals when the applied pressure is 1 bar. All right. What is the vapor pressure when the applied pressure is 20 megapascals? Right. So a few things we need to do in order to get things prepped. Right. Obviously, 20 degrees Celsius is not going to happen, right? We need to have 293.15 Kelvin, right? Hopefully that should be always super true, right? We have different units of pressure. We have kilopascals, megapascals, and bar, right? Well, the best way to do it definitely is going to be changing bar into pascals, right? Remember that 1 bar is going to be, what is it? Always have to remember this. 100, 10, what is it? Always have to look it up, which again will be given to you on the exam for sure. All right, let's see. Oh, there we go. 1 bar is 10 to the 5th pascals, right? Right. 1 times 10 to the 5th pascals. That's what I thought it was. Right. And then for our molar volume, right, one thing you have to keep in mind is that we're going to be using R here. Right. We're going to be using R, which means that our molar volume needs to be in cubic meters instead of cubic centimeters. Right. So if I take 18.1 centimeters cubed per mole, right, change it to meters, you're going to divide by 100, right, divided by another 100, divided by another 100, right? This becomes 1.81 times 10 to the negative 5th meters cubed per mole, right? We had to fit it around arm. And we're going to use a normal 8.314 arm just to make it easy on ourselves. All right. Now, let's look at our equation here. All right. So we have Vm over RT, right, times delta P equals the natural log of P over P naught, right? Normal vapor pressure. Right, so we have basically all these numbers that we need. All right, Vm we know is going to be 1.81 times 10 to the negative fifth. R is going to be 8.314. T is going to be 293.15. Right, for our change in pressure, again, this is the change in the overall pressure. Right. Well, the applied pressure is 20 millipascals, right? And it changes from 10 to the fifth basically to 20 millipascals, which is, or megapascals, I should say, which is 20 times 10 to the sixth pascals, right? Well, the difference here is going to be 20 times 10 to the sixth minus 1 times 10 to the fifth. Get that correct. 1 times 10 to the fifth. Right. This is going to be the natural log. We have our new vapor pressure on top and the original vapor pressure, which is 2.34 kilopascals. Right. Now, let's take the left-hand side and simplify things. All right, so all of this becomes 1.81 E negative 5 divided by 8.314 times 293.15. All right, all of this becomes 8.27 times 10 to the negative ninth, right? Our delta P is going to be 20 E6 minus 1 E5, which is going to be, yes, 1.99 times 10 to the seventh, right? Because 20 times 10 to the sixth is 2 times 10 to the seventh, right? And all that is going to equal the natural log of everything over here, right? Natural log of P over 2.34 kilopascals. We're going to keep the units. That way we know what units are in values going to be. All right, the left-hand side is 1.99 times 10 to the seventh times 8.27 E negative 9. All right, this entire left-hand side becomes 1.64 times 10 to the negative first. Natural log of P over 2.34 kilopascals. Right. And then from here, we would need to take E to the power of both sides. Right. If I do E to that and E to that, right, that'll cancel out the negative logs. And go over here. All right, let me see. E to the power of 1.64 negative 1 is going to be 1.178 and do 1.178 equals P over 2.34 kilopascals. And when you do that, our new vapor pressure is going to be 5.04 times 10 to the negative first kilopascals, right? Or basically 0.5 kilopascals. Right? Most of the work was in doing all the conversions, right? But again, this is the reason why I tend to like this equation more. Like, look how much of the work you got done just doing all this stuff before we even got to the E. I like leaving E for the very end when everything is super simple. I think it's easier to work with. But anyways, that's what our new vapor pressure would be. All right, what our new vapor pressure would be. Okay. So going on from there. Let me think. Let me see real quick. E to the negative 1.6 equals that. Yeah, that makes sense. Okay. Now, if we're looking at our phase boundaries between two different phases, right, they have to be equal chemical potentials at equilibrium, right? Mu is equal to G, and G is equal to, or DG is equal to VDP minus SDP, right? And then we can set these two equations equal to each other, right? We have phase one on the left and phase two on the right, right? If we rearrange them to put S's on one side and V's on the other side, right? Then S, basically, if we have like S, 1 minus Sm of 2. This is the same thing as the entropy of the transition, right? Going from one phase to another. This is the delta S of the transition. Same thing with the molar volume. It's the change in the molar volume of this transition. Right? And if we rearrange this, we get the Clapeyron equation. It's going to be dP over dt equals delta S over delta V, both molar, of this transition. All right, and again, dP over t, this is going to be a slope, right? And our delta S and our delta V are going to be both numerical values, right? And so we get an equation for a slope. All right. Now, a slightly more practical version of this is going to be its inverse, where we flip everything. Right? We have dt over dP is equal to delta V over delta S, right? So this allows us to relate a change in temperature of a phase change, right? So we can see that if we change the pressure, how much is, or how is the boiling point or melting point or something like that, or sublimation point, how is that going to change, right? That's a little bit more useful, right? But this first Clapeyron equation is going to be the basis of where we derive a little bit more stuff in the rest of the chapter. All right. So for melting and fusion, right, which is again going from solid to liquid, right, our delta V is going to be very small. Right, it's going to be very, very small. Let's go back and look. So this is again dt over dp equals delta V over delta S, basically. Right, so since delta V is very small, right, you expect if we increase the pressure, it's going to have a very small effect on the melting point, right? Because if this is a small number, then our slope is going to end up, this is a small number on top, this is a bigger number on bottom, right? We're going to get a very big slope because we're not going to change temperature very much as we change pressure, right? So we get a very steep slope here between solids and liquids, right? Again, if we increase the pressure like this, right, we end up with a not a very large increase in temperature to go back to the line, right? With vaporization and sublimation, though, right, vaporization going from liquid to gas, right, sublimation going from solid to liquid, right, these we'd expect to have a very large increase in the molar volume, right, because we're going from condensed phases to gaseous phases, and the gaseous phase is going to take up the entire space of its container, basically, right? Going to take up a whole lot more space, right? So because of this, yeah, dt over dp, v delta V over delta S, right? If we have a large change in our volume, then we would expect our pressure to have a larger change on our temperature. So what we see here, right? We look from liquid, this vaporization right here, right? We increase the pressure a little bit, results in a large increase in the boiling point, right? Large increase in the boiling point. Same thing we see here for sublimation, increase the pressure a little bit, large increase in the sublimation temperature, right? The sublimation point, I should call it that. Right? That's what we're seeing. It's all based off this Clapeyron equation, or the inverse of it in this particular example here. But it's the same difference, still the Clapeyron equation. Right? Now, if we wanted to do actual math for our slopes, we're going to start with the regular Clapeyron equation. Right? Now, delta S is, of course, kind of a pain to measure sometimes. Right? Delta S is not always great. Right? So what we can do is remember that delta S is equal to delta H over T. Right? And we're in a particular transition. These are all TRSs. And so we can sub in H over T for S. Right? And we do a little bit of slide rearrangement. Now we have pressure on one side and temperature on the other side. Right? Maybe from here you can see how these things are going to progress. Now, we're going to start from here. Now, for our fusion, right, solid to liquid, we can assume that delta V will be very small. And we're going to assume that it's going to be pretty much constant. Right? It's not going to be exactly constant, but for what we care about, like in terms of, it's going to be a very good approximation, right? We can treat it as constant. Right? So the left-hand side is going to be dP. The right-hand side is going to be H over V times dt, right? Or 1 over T times dt. Right? If we integrate both these sides with respect to their different variables, right, dP going from initial pressure to a final pressure is going to be the difference, right, or delta P basically, right? This is basically delta P of our vapor pressure here. Sorry, not the vapor pressure, well, the pressure in general. And this is basically delta P on the left-hand side, right? H is a constant. It's being treated as a constant over this temperature change range, all this particular stuff over this pressure range, right? Delta V is so small, we're going to treat it as a constant. And so we're just going to have the integral from T1 to T2 basically of 1 over T, which is the natural log of T over T naught, or, T2 over T1, however you want to say it, right? Now, T doesn't change very much in a fusion transition because we just saw that, right? We saw in fusion that as we increase the pressure, the temperature doesn't change very much. All right, so the book does a little bit of extra math stuff to use math and identities and all those other things to change this equation into this one. Something a little bit easier, right? It's basically the same, but note here we have T on the bottom, or T star, the initial temperature, right? And instead of natural log, we have T minus T star, or T naught, or T star. That's the way I should be saying it, right? So basically here, this is our change in temperature, right? Again, so we basically have a change in pressure. This is a change in temperature. The key thing to remember is that there's the initial temperature in the bottom, right? Now, again, we can use this. Benzene freezes at 1 atmosphere and 5.5 degrees Celsius. Its mass density changed from 0.879 to 0.891 grams per centimeters cubed. And the enthalpy of fusion is 10.59 kilojoules per mole. Estimate the freezing point at 1,000 atmospheres, right? At 1,000 atmospheres. So we still have the same basic idea, right? We have P minus P star, right, equals delta H over T star delta V, right, times T minus T star. Okay? And we're basically looking for what is the value for T. right? And T star is going to be at 5.5 degrees Celsius. Okay. So going from here, all right, let's start plugging in some numbers. All right, we're going to do plug in numbers first, and then we're going to change numbers when we need to. Okay. So our new pressure is going to be 1,000 atmospheres, right? And our initial pressure was 1 atmosphere. All right. Delta H, we are told, is 10.59 kilojoules per mole, right? I'm going to go ahead and change that from kilojoules into joules to say 10,590 joules per mole. Right. Our T star, our initial temperature is 5.5 degrees Celsius. Well, obviously, Celsius is a crappy unit. Right, we're going to change it to Kelvin. That is 278.65 Kelvin, right? Times our change in volume. Right? This is where the little wrinkle in the question comes from, because we're not given a straight number for the change in volume, right? The molar change in volume. All right. But what we can do is do a little bit of side math to figure this out, right? So if we have 1 mole of benzene, all right, benzene is C6H6, right? That's going to be a molecular weight of 78, right? 12 times 6 plus 6 is 78 grams per mole, right? So let's assume that we have a full mole of this, because this is going to be, again, these are molar values here. Molar volume, molar enthalpy. All right. In that case, we can actually we'll just get rid of that molar entropy thing right there. Right. So we're going to assume this is a mole of it. So if we have 78 grams, right? Oop, go back. All right, 78 grams. Initially, this 78 grams takes up 0.879 grams. Whatever. You know what I mean. Division. Right. Takes up 0.879 grams per centimeter cubed. Right. And so 78 grams in the initial density would comprise 88.7 centimeters cubed, right? 88.7 centimeters cubed, right? For every 1 mole, right? That's basically what we're saying here. 88.7 centimeters cubed for every 1 mole. All right, let's go ahead and change this into meters, just to make things nice and simple. All right, so this is going to be 8.87 times 10 to the negative, let's see, 88.7, right, divided by 100, divided by 100, divided by 100 is 8.87 times 10 to the negative fifth meters cubed per mole, right? If we do the same thing in the second instance, right, we still have that same 78 grams, 1 mole, right? But now our new density is 0.891. If we do that, okay, then our new molar volume is 87.5 centimeters cubed per mole, right? Or 8.75 times 10 to the negative fifth meters cubed per mole, right? And so our delta V here is going to be the difference between the two, right? Let's do 8.87 minus 8.75. This is going to be, we'll call it 0.12 times 10 to the negative fifth meters cubed per mole, right? That's the one little wrinkle in this question. right? So take this number, put it in here. But we're looking for the new temperature. We know the initial temperature is 278.1 or 65. All right. From here, let's do a little bit of math. We're going to simplify everything as much as we can. So the left-hand side is going to be 999 atmospheres. Right. Everything in the middle is going to be 10,590 divided by 278.65 times 0, 0.12 e negative 5. Right. If I do that, everything in the middle comes out to be, it looks like correct, 3.16 times 10 to the 7th. Right, again, it looks weird, but that's what it's going to be okay. And then we'll keep t minus 278.65. Right. Now, at this point, this will give you a good clue as to what you should be doing next, right? Because if you try to divide this, you're going to get a very, very, very small number, right? Well, actually, you can't do this, but what we're going to do, we're going to change our atmospheres into pascals, just to be like super duper sure, right? This was used using all of our SI units, like made using all of our SI units. So let's use pascals to make sure we're 100% true, right? So 999 atmosphere is equal to 1.01 times 10 to the 8th pascals. Did that real quick. All right. Now, if we do a little bit of division here, right, that number divided by 3.16 E7 is going to be 3.2, just 3.2 basically, equaling T minus 278.65 Kelvin. All right, you do that a little bit. Our new temperature is going to be 281.8 Kelvin. All right, that's going to be our new freezing point, right? Our new freezing point, it went up just a few degrees. It went up 3.2 degrees, right? And keep in mind that the pressure increased drastically, right? We increased the pressure 1,000 times over, right? So, for what we see here, this is a very small, 3.2 degrees of increase over 1,000 atmospheres is quite a small amount. Okay. Now, if we do the same thing, but for vaporization, right? Same thing, but for vaporization. So the volume of our gas phase is much greater than the liquid phase, right? Generally speaking, assuming the pressure is not incredibly high. So our delta V is going to be approximately equal to the molar volume of the gas. Right? But again, we know that our molar volume is going to change greatly with our pressure and temperature. So instead of integrating the molar volume, which is going to have much more variability to it, right? We're going to put it in terms of P and T, right? We know that molar volume is RT over P, right? So we plug this in for our molar volume. We get this sort of arrangement here, right? P delta H over RT squared, which is the Clausius-Clapeyron equation. We rearrange it a little bit, and we'll get this version, which is dP over P equaling delta H over RT squared times dt. Right. If we integrate this, both sides respective to their variable, right? The integral of dP over P from basically P1 to P2 is the natural log. We've seen that before, right? P over natural log of P over P star, or P2 for P1, however you want to do it, right? Delta H is the constant we're bringing out. R is the constant we're bringing out, right? And then the integral of 1 over T squared with respect to T is going to be negative T over 1, or negative 1 over T, right? Negative 1 over T. This is where the negative comes from the integral of this. Right? Don't forget the negative, it's pretty important. Right? We have negative coming out, and 1 over T over these limits is 1 over T minus 1 over T star, or 1 over T2 minus 1 over T1, however you want to say it. Right? Now, this particular equation here is going to work for both sublimation and vaporization, right? Because in both scenarios, we can assume that the change in volume is going to be approximately equal to the molar volume of the gas, right? So we're going from a condensed phase to a gaseous phase. So it's going to be functionally equivalent. All right, now if we do this one, right, the difference between the normal boiling point, which is that 1 atmosphere, and the standard boiling point, which is that 1 bar. This is a very, very, very small difference, right? Right. At the normal boiling point, the enthalpy of vaporization is 40.7 kilojoules per mole. And again, we're going to assume that this is going to be true. Right. So our left-hand side was natural log of P over P star. Right. And then we had delta H, negative delta H over R times 1 over T minus 1 over T star. Okay, so let's start putting these things in. Now, for our pressures, here's the main thing, right? This is in atmospheres, this is in bar. We can't just put those in willy-nilly because they're two different units. We can't do that. So what we need to do instead is to express them in terms of a more common unit, which is going to be pascals, right? So 1 atmosphere is going to be 101,325 pascals. And 1 bar, as we talked about before, is basically 100,000 pascals, right? A very, very slight difference, but this is what we're going to be doing here, right? Now, let's see. There's no particular rhyme or reason as to which one we call the normal, like if normal is P or P star. What I think I'm going to do is we'll make the normal boiling point, we'll make this one the star, and we'll make the standard boiling point the non-star. It doesn't really matter all that much, right? Because it would work either way. But this is where we're going to go with. So natural log, all right, P non-star is going to be 100,000, right? P star, we call the normal boiling point, that'll be 101,325. Right. Negative delta H is going to be 40.7 kilojoules per mole, or 40,700 joules per mole. R, we'll keep it 8.314. Right. On the inside, we'll have 1 over T. We don't know what the new temperature is going to be. Actually, we do. Sorry. Yeah, we don't know what the new temperature is going to be. But we do know the old temperature is the normal boiling point of water, right? Which is just going to be 100 degrees Celsius, right? Or 373.15 Kelvin. Right. So on the left-hand side, the natural log is it? Nope. Natural log. There it is. Natural log of 100,000 divided by 101,325 is going to be negative 1.31 times 10 to the negative second. Right. Negative stays here. If we do 4,700 divided by 8.314, we will get 4.89 times 10 to the third. All right, we're going to keep all this in here. 1 over 373.15 is 2.68 times 10 to the negative third. We'll simplify that one a little bit. All right. Now let's start doing our division stuff. Right. If we divide both sides by negative 4.89, well, if we do negative 1.31 e negative 2 divided by negative 4.89 e 3, right, we would get 2.67. Let's do 2.68 times 10 to the negative 6 equals 1 over t minus 2.68 times 10 to the negative third. And then from there, fix this up a little bit. 10 to the negative 6. Right. Do a little bit of addition. 2.68 times 10 to the negative third plus 2.68 times 10 to the negative 6, right, is going to be, we're going to do some extra decimals here. Otherwise, we're going to get basically the same temperature. It's going to be 2.6827 times 10 to the negative third. That equals 1 over t. If you solve for t, t is going to be equal to 1 over that answer. 1 over that answer. This is going to be 372.7 Kelvin. All right. So the difference here, we went from 373.15 to 372.7. So we basically changed the boiling point. What is that? 0.45 Kelvin. Right. So our delta T here would be like 0.45 Kelvin. Right. Which makes sense, right? Because we're going from, we only changed it basically 1,000 pascals. Right. So it's going to be a very, very small change in the boiling point. Right. But this is how we would do it. Right. Use this particular equation here. Right. Always be careful when we have these fractions. You know, fractions are always kind of annoying to deal with, even though we've been doing them for years and years and years and years. Right. You learn fractions initially in like 6th grade or something like that. And you've been doing it for a super long time, but they're still pretty annoying. So be careful about that. Now, that being said, this is the last bit of the chapter. That's all you need to do it, right? It's pretty a very straightforward chapter. But let me know if you have any questions. You know, exam 2 is going to be just topics 3 and 4, right? First or second and third law plus this phase transition stuff. So that's where it's going to be at. Okay. See you later.